Welcome back. In this video, we're going to begin learning about the solution process. We're going to start by looking at what is meant by a solute, solvent, and a solution. We'll identify the types of intermolecular forces that are formed and broken when a solute dissolves. We'll also identify enthalpy changes, both endo and exothermic, that are part of the dissolution process, and then also discuss the factors that occur to make the dissolution process occur spontaneously. So you might have heard it said that if you're not part of the solution, you're part of the problem. But in chemistry, we prefer to say that if you're not part of the solution, you're part of the precipitate. With that, let's talk about what a solution is. So a solution is a homogeneous mixture. What that means is that there is uniform mixing throughout, and that the properties of that solution are the same. So if you were to take a sample of a solution, it wouldn't matter if you took it on one end, on the other end, or somewhere in the middle, you should get the same properties and the same identity. When we talk about solutions, we need to talk about the solute and the solvent. The solute is a minor component of the solution. It's what makes up a small portion of the total, whereas the solvent is the major component in a solution. In Chem 110, we're going to focus on aqueous solutions. This is solutions where water is the solvent. However, there are a variety of other types of solutions that you should be familiar with. We can have solutions where both the solvent and the solute are gases. The most common example of this is air. We also have solutions where we have solvents that are liquid, and the solute is a gas. That's a carbonated beverage. Then you can have liquids in liquids, such as an ethanol in water or alcoholic beverages. If you take a solid and put that into liquid, that is another type of solution. A common example of that is putting sugar in water. A fifth type is where we could have a gas solute put into a solid solvent. And this is in the case of hydrogen gas being absorbed by palladium metal on catalytic or different kinds of converters. You could have a liquid solute and a solid solvent. This occurs when you take liquid mercury and put it into silver fillings. And then finally, a solid solute and solid solvent, such as in steel alloys. So now let's talk about, again, in Chem 110, we're going to focus on liquids as our solvent phase for different types of solutions. But what's happening on the molecular level? Let's take the example of salt, table salt, and sugar. So what happens when they're dissolving in water? Well, if you look at the salt crystals, it's an ionic compound. What we see is that ionic compounds will dissociate in water, but for the most part, molecular compounds do not. So what does that mean? Well, if you take a look at a crystal of salt, we have the positive and the negative charges. And when you place that in the water, two processes occur. One of them is called dissociation, and the other is called dissolution. Now, if we compare that to sugar in water, the sugar molecules are made up of covalent bonds between the carbons, hydrogens, and oxygens, and intermolecular forces keeping the molecules together. But if you put that in water, each molecule of sugar still stays together within itself, but each molecule is broken apart from the other sugar molecules. And so we can see that there's a difference between the dissociation process, which breaks apart ions, and the dissolution process. And dissolution, also known as solvation, occurs when the solvent surrounds the solute. So we see in both cases, salt and water and sugar and water, we have dissolution. The water molecules are surrounding the solute. But for ionic compounds, we also have dissociation. Let's now look at the energy changes that are occurring when the full dissolution process occurs. let's say that we have a solvent and a solute. And for the purposes here, it doesn't actually matter if we're talking about an ionic solute or a molecular solute, because what we see is one of the first steps is to break the solute-solute interactions. So if it's an ionic compound, that would be breaking apart into ions. If it's a molecular compound, then it's breaking the molecules apart from each other. And that requires an input of energy. We also need to break the solvent-solvent interactions. So if we're dealing with water-based solvents, that would be breaking the hydrogen bonding, the dipole-dipole interactions, and the London dispersion forces that exist between the water molecules. Again, because we're breaking bonds, breaking intermolecular forces, this requires an input of energy. Then we are going to form interactions between the solute and the solvent. And this releases a large amount of energy because we're forming interactions. We're forming intermolecular forces that are attractive, and therefore that releases energy into our surroundings. The sum of the enthalpies we term the enthalpy of solution. So each of these three steps we can see results in a total enthalpy change of our solution. And in this example, we see that it is exothermic. Now let's take a specific example of water dissolving a salt. When ionic compounds dissolve in water, we form ion-dipole interactions, and this creates a solvation sphere. So for sodium chloride in water, we're going to first break the ionic interactions between sodium and chloride ions. Then we'll break hydrogen bonds between the water molecules. We also break other dipole-dipole interactions and London dispersion forces. And then finally, we're going to form ion-dipole interactions between each ion and the various water molecules. Notice that for the cations, for sodium cations, the negative ends of the water molecule are interacting with the cations, and with the anions, the negatively charged anions, we see that the hydrogen portion of water is interacting more closely with the anion. And it does that in order to balance out the charges. Let's talk a little bit more about some properties of solvation. Solvation is a reversible process. If you're to evaporate a solvent, this would obtain back the solute in a pure unchanged form. So what we see then is that the solvation process or dissolution is not a chemical reaction, but it's a physical process. For example, if we dissolve sodium chloride in water, we obtain solvated sodium ions and solvated chloride ions. However, if you take and you react iron with hydrochloric acid, we end up with iron chloride. In both of these cases, if we evaporate the water off, we see that there's a different final product. For the sodium chloride solution, we would end up with sodium chloride back. However, for the iron chloride solution, we don't get the same reactants we had to begin with. Therefore, we can distinguish between physical changes and chemical changes. Now, what causes the dissolution process to occur? It's because the intermolecular forces that are formed when the substance dissolves are more favorable than with the two substances on their own. And generally speaking, we use the term like dissolves like. So when you have polar molecules and salts or ionic compounds, those will dissolve well together. So this is an example of sodium chloride or sugar dissolving in water. Both of those are polar or ionic, and water is polar. However, if we have non-polar substances, those mix well together. So for example, you can mix a variety of oils together. And when substances mix in any proportion, so you can mix any number of oils together and you can have a roughly even amount or large amount of one oil, large amount of the other oil. We call those, we deem those miscible if they can mix in any proportion. However, If we try and mix substances of different polarities together, we see that they don't mix well. That would be an example of we could mix oil with water and they will separate out because they don't dissolve well together. Another important aspect of this dissolution process is that our reactions can either be endothermic or exothermic, depending on the amount of energy that is given off when the solute and the solvent combine together. If the energy given off is greater than the sum of the energy that's put in to break the intermolecular forces, then it's an exothermic reaction. However, if the enthalpy given off during the third step is smaller than the sum of the two steps, then it's an endothermic reaction. Let's talk about why endothermic processes might occur. It turns out that enthalpy is only one part of the picture. We have to account for other aspects as well. So a process is going to occur spontaneously or on its own when energy is released, therefore it's exothermic, but also if there is a large increase in disorder, also known as entropy. And these two factors balance each other out. We can have an endothermic process, so a process that requires energy, but if it creates enough disorder, then that reaction will occur on its own. And so, for example, if we take carbon tetrachloride mixed with hexane, this process is endothermic. However, because there is a high level of disorder that occurs, then these processes, then the dissolution process will still occur. And so what we can see is that a process can be endothermic, which normally is unfavorable. But if the increase in entropy is large enough, then the process will still occur on its own. That's it for this video. Thanks for watching. Have a wonderful day.